processes that happen in our universe that we cannot really see at optical wavelengths at all. And this plot shows a variety of phenomena that only can be studied by radio astronomy. Things like pulsars, which are these incredibly compact remnants of dead stars that are spinning around so rapidly, and they have this beam of radio light that sweeps across the Earth repeatedly, creating these very regular flashes that can be detected at radio wavelengths. In the center is actually a picture of Jupiter, and this is allowing radio waves allow us to view its magnetic field, because electrons in the magnetic field spiral around them, and when they do that, they emit radio light that we can detect here on the ground. What's shown in the far right is the remnant of an explosion where a massive star blew up at the end of its life, creating this ever-expanding cloud of emission that again is our gas that is again emitting at radio wavelengths. Even on galactic scales, we can see these incredible things that had never been seen before. These are jets that are hundreds or thousands of times larger than a galaxy, which is located here. And the jet from the supermassive black hole in the center of this galaxy has accelerated gas to enormous speeds, pushing it way out into the extragalactic environment, creating these big lobes of radio waves. And also, radio astronomy is also good at detecting magnetic fields, which is a crucial component of understanding the physics of the universe. And then lately we have this mysterious phenomenon called fast radio bursts, in which enormous amounts of energy are released in just a tiny fraction of a second. And this is a relatively new phenomenon that has only been detected in the last few years. Yeah, go ahead.
I will picture the top.
Yes.
Is that like the...
Well, it's actually it's like a dipole, and it's a ring of emission, a ring of electrons that are bound in a ring around Jupiter. So.
With the galaxy jets?
Mm-hmm.
Is that what's at the tail end of the pulsar, or is that?
So the galaxy is located right here, and deep in the center of this this little dot here. And so at the black hole, gas is streaming in, and some is deflected out at vast speeds that blow out into the surrounding extragalactic medium. Okay? All right. So radio astronomy has actually been, was actually discovered by accident. And it was discovered by accident by this person named Carl Jansky, who in the early 1930s was working as a Bell Labs engineer in New Jersey. And he was given the task of trying to understand sources of noise that were occurring in their experiments to try to establish transatlantic communication. And so he built this contraption, which is an antenna about 30 meters long and 6 meters high. And by being on a merry-go-round, he could like turn it and try to locate the sources of these this interference. And he did detect interference from thunderstorms near and far, but he found an ever-persistent source in the sky that at first he thought was the sun, but then it was found to be moving to the west throughout the year. And it turned out that what he was detecting was actually the supermassive black hole in the center of our galaxy called Sagittarius A star, a 4 million solar mass black hole that's surrounded by a disk that's emitting radio waves. And it was totally unexpected. This made a lot of news, and this technically, I guess, makes this the world's first 30-meter telescope. But it is still an incredible thing that this person just sort of stumbled on to the idea that there were sources of radio emission in coming from beyond the Earth's atmosphere. Interestingly, Karl Jansky was very excited about this, but he wasn't able to continue studying it. He was actually reassigned to do something else by his employers. And sadly, he actually passed away at a relatively young age, so he wasn't really able to continue this line of research. But the banner was taken up by this man, Grote Reber, who is arguably the world's first radio astronomer. When the news of Jansky's achievement was announced to the world, he was quite excited. And he actually applied to work with Jansky at Bell Labs, but was rebuffed because Bell Labs was more interested in commercial applications. It was the Depression. So he said, well, I'll just do it myself. And he built this 8-meter radio antenna in his backyard in Wheaton, Illinois. And he spent many months basically just having it go around or having it track the emission on the sky. And he had a few false starts with various receivers, but he finally hit one that worked at about a 2-meter wavelength. And so with this incredible homemade telescope, he was actually able to track some of the world's first known radio sources, things like radio sources like Cygnus A, which incidentally is this, Cassiopeia A, and Sagittarius A, which is that source in the bottom there. So he was actually the world's only radio astronomer for 10 years. And it was after World War II that a generation of electronic engineers were able to build upon the vast leap of technology that occurred during the war due to the development of things like radar. And then big money started coming into studying radio astronomy. And it was this sort of ignited the development of radio astronomy worldwide. And the Commonwealth countries actually were quite good at developing radio astronomy, Canada, Australia, and England, or the UK in particular. And here in Canada, Canadian radio astronomy is basically, its history is summarized in this one slide. And I'm doing a disservice to the decades of work that are behind Canadian radio astronomy. But nevertheless, for completeness, let me say that there were 2 radio observatories established in Canada. The first is the Algonquin Radio Observatory in Ontario, which was established by that man named Arthur Covington. And it was established in around 1960 and led to the development of this 46-meter antenna, which was in service for about 25 years. And then here in British Columbia, the Dominion Radio Astrophysical Observatory was constructed by these 2 people. One on the left is John Galt, not the man from Atlas Shrugged, but John A. Galt. And the man on the right is Jack Locke. And they constructed the DRAO site, which is still in operation today. John Galt helped build the antenna that now bears his name, the Galt 26-meter antenna. And then in about 1970 or so, this array of telescopes where individual radio antennas have their signals combined electronically to form a single radio facility was constructed. Now, the Algonquin telescope and the Galt telescope are particularly notable because in 1968, they demonstrated that you could combine radio signals from antennas that were separated by thousands of kilometers to produce basically the response of a single telescope thousands of kilometers wide. And this was called very long baseline interferometry, and Canada was the first to do it by combining the signals from these 2 telescopes. Now, sadly, the 46-meter telescope was decommissioned in the late 80s. Canada then joined the James Clerk Maxwell telescope in the late 80s, which it was a partner in for over 25 years. This is more of a high-frequency radio telescope. But the solar flux monitor, which is shown there in the lower right, began here at the Algonquin Observatory, and it has continued to observe the sun every day, and it has done that since 1947, where it has observed the sun at the wavelength of 10.7 centimeters, providing an incredibly long baseline of monitoring of the sun's output. And this actually has quite interesting implications in space weather, and people use it for things like examining how the influence of the sun might affect things like pipelines and things like that. Is one of Canada's little known but incredible scientific outputs, this one solar flux monitor that's still in operation today, now at DREO, where it was moved to in 1990 or so.
Where are they each located?
So Algonquin is located in Algonquin Provincial Park. So it's located about a couple of hours to the west of Ottawa. DREO is located in Caledon, British Columbia, which is just south of Penticton. So you can go visit there today if you want. Okay, so now this, of course, is quite an amazing accomplishment for Canada over the decades. But you may notice that there's really nothing new here, right? Nothing new has really been established here. Well, maybe this is something different, but in the low frequency radio astronomy regime, there has been nothing new for almost 50 years. Now that's not quite true because that's largely because the development of telescopes like this, which is the Jansky Very Large Array. This is also like the synthesis telescope, a combination of individual antennas that are electronically combined to become a single instrument. And when it began operation in 1980, it effectively became the dominant telescope for low frequency radio astronomy in the world. It's run out of New Mexico, and it has been an incredible resource for radio astronomers since it began in that time, almost now over 40 years. But since then, there has been little for Canada itself to have in the regime of radio astronomy, though I will say that Canada did provide a new correlator for the VLA, as it's called, about 15 years ago, which a correlator is the supercomputer that combines all of those individual signals from the antennas. And with its modern design, the people, my colleagues at DREO, were able to build this new correlator and install it, vastly increasing the aging Very Large Array's capabilities and modernizing it. I'd just like to go back, though, here and give a shout out to this, because if you're interested in the history of radio astronomy in Canada, good news, because this book is about to be published in about a month. And it's been a long time coming, and some of you may recognize Elizabeth Griffin, who is one of our astronomers here at DAO, as the second author of this book. Jasper Wall is an astronomer over at UBC. So this book is going to be quite an event when it comes out, because it finally tells the story of radio astronomy in Canada far better than I just did. But radio astronomy in Canada, yeah, you can buy it on Amazon. So pre-order it today. Okay, so
We'll get some.
okay, all right. So now, I won't say that Canada has been sucking fumes for the last 50 years, because there has been some innovation, and largely this has been at DREO, where most recently we've had the development of something called the Canadian Hydrogen Intensity Mapping Experiment, called CHIME for short. And it consists of these 4 strange half-pipe antennas, which signals fall in, and basically it points straight up, and as the Earth turns, it's able to record radio emission above, in the line directly above it. And it is doing an amazing job of detecting a lot of those fast radio bursts that I mentioned before, and it's really put Canada on the map for detecting such things, because it has detected most of the ones that are known.
What's the hydrogen?
Sorry?
How is the hydrogen?
Oh, so when it was originally conceived The idea was that it would look for that hydrogen emission. Remember the galaxies that I showed you before that comes strictly from hydrogen gas? And it's looking at it at great distances. And so it's looking at it at the intensity of the hydrogen emission. So that's where the H comes from in this. Okay, so after that long preamble, here we are finally to tell you that Canada has a new radio observatory, the Square Kilometer Array, or SKA. And the rest of my talk is going to be just about SKA because it's very exciting. SKA is actually two observatories in one. There's something called SKA Low, which consists of forests of these dipole antennas that are located in Western Australia. And then on the right, there are these collections of individual antennas, dish antennas, that are spread out across a desert region in South Africa. Now, even though they are geographically separate and they are looking at different wavelength ranges, it's still one observatory. So the SKA has been in the works for a very long time indeed, almost 30 years. When it was, I first heard about it in the late 1990s. Well, it was actually very exciting for many countries because the idea was to build the world's largest radio telescope. And astronomers in Canada have been quite keen on it for many years, and there have been these various decadal surveys called the long-range plans, where the priorities of the community are established for the next 10 years. SKA has been near the top of this since the very first one in 2000. And this comes directly from the document from the one that was just published a couple of years ago, where it says Canada's highest priority for radio astronomy should be to fund and participate in the SKA design baseline construction. Amazing. And it recommends an overall level within the project of 6%, which doesn't sound like a lot, but it's still, when you're looking at how different countries, it's a multinational project, not one country has a dominant share really in it. So yes, with this recommendation, people have been working to have Canada join the project. And this shows the global distribution of the countries that are interested in being part of it. Those that have asterisks beside it are full members. And the ones that are shown in blue are those that are either full members or so-called observers, which haven't yet formally joined the project. The headquarters of the project is actually located in the UK near Manchester at Jodrell Bank Radio Observatory. And you can see that there are places all around the world, Australia, China, India, much of Europe, Canada. And I'm happy to say that, and of course, South Africa and many African countries are also quite interested in the project. And I'm happy to say that just this past January, Canada announced that it will indeed join the project. This is a copy of a news release that came out in early January, straight from the National Research Council, saying that yes, we're actually finally going to do it, and we're going to spend almost $270 million over the next 8 years to help fund its construction. And then we will continue funding its operation for years afterwards.
I think that a site?
Yes.
Where is it?
Well, it's going to be, as I said, the low frequency version is going to be in Western Australia. And the mid frequency region one is going to be in South Africa.
Oh, so
They're not building anything in Canada, but that's because you want to build these things in extremely radio quiet places where there's not a lot of radio interference. So these places are really very, very remote. And so they are really the best sites in the world for building radio telescopes, considering the sheer amount of terrestrial sources of radio emission out there. Okay, so here is some technical information about the telescopes. The SKA Mid, the one in Africa, is actually going to have a frequency. Oh, I actually did this. I changed it to wavelength for you. It will go from wavelengths of 86 centimeters to 2 centimeters. And then the one in Australia will go from 6 meters to 85 centimeters, covering basically almost all of that window in the atmosphere that allows us to detect radio waves. And yeah, there will be almost 200 of these antennas for the SKA mid. Each one will be about 15 meters across. And they will be spread out in a configuration where the maximum baseline will be 150 kilometers.
Are they the same boxes?
Close. And then for the SKA low, it will consist of 131,000 of these dipoles arranged in stations, of which 256 are clustered together, and then those are spread out around the Australian outback and combined together over a maximum baseline of about 74 kilometers. Yep.
In Australia,
Yes.
if there's so many of them over a very large space, has there been some pushback from some of the Aboriginal groups of their land?
I will get to that. And in fact, I will just tell you that the SKA has done a very good job of engaging Indigenous peoples in explaining the social and economic benefits and having them as partners early on. So yes, yeah, no, there has been no pushback on either site, and that's a very, very welcome thing. And I'll just get into that a little while later. So this is an extremely busy slide that the SKA produced to show how very big they are. But basically, what's left to right goes from low to higher frequency radio astronomy. And then you can see just in terms of the square footage or the square meters of aperture each of these antennas or each of these facilities has, how much bigger the SKA is going to be. So the SKA low, with its 131,000 antennas, will have basically 419,000 square meters of surface area. The SKA mid, because it will have about 200 dishes, will have about 33,000 square meters. And you can see how that relates to other facilities here. The VLA itself only has about 13,000 square meters of surface area. So this plot shows how detailed the different observatories in the world are at different wavelengths. And the SKA and other radio observatories are shown in orange here. And basically what this says is that with greater or with shorter wavelengths, your ability to see details increases. You can see the peaks of these triangles are very similar in each of these regimes, where you have radio waves and you have microwaves and you have infrared and optical on the far right. And so this basically shows how the SKA-1 will have resolution, as it's called, of comparable amounts to even optical and microwave observatories around the world, which is good because when you're looking at something at one wavelength, you want to be able to see something with similar detail at another. This plot shows how much more sensitive the SKA will be compared to individual existing antenna or facilities. And in gray are facilities like the JVLA, the Jansky Very Large Array, and the blue shows basically the sensitivity comparison where upper or higher is better. And so the SKA-1 will be basically an order of magnitude more sensitive than the VLA over a very wide range of wavelengths. Now you may wonder, what's that orange band up there? This says SKA-2. I'll get back to that later. Okay, so what will it look like? Here is a video showing what the SKA low will look like, at least at one of its stations. This sort of reminds me of the Charlie Brown Christmas special where Linus and Charlie Brown go and pick up a Christmas tree and banging on the metal trees. But anyway, these are actually these specially designed dipole antennas, and they have this Christmas tree-like appearance because each length corresponds to a certain range of wavelengths that it is sensitive to. So having a wide variety in a tree-like shape gives it sensitivity over a wide range of wavelengths. So this is in a place called, I'm going to screw this up, Inyaramana Ilgari Bundara in Western Australia. This apparently means, that I'm paraphrasing, where the sky meets the stars in the local dialect. Now here's a video showing the situation in Africa in the desert called the Karoo Desert. This is actually some existing antennas in South Africa in a facility called Meerkat. SKA Mid is going to build out of Meerkat like that. So its dishes are very distinctive. And the SKA is in the process of constructing newer antennas there right now. So what about the science? What is SKA going to do? Well, remember that slide way back where I showed all of the things that radio astronomy you can see? The SKA is going to be able to do that and way better because of its higher resolution and its higher sensitivity. But then there are new things that its inherent sensitivity and resolution will allow. And one of them is probing the epoch of reionization, which is a particular time in the universe's history where the first stars and galaxies were formed. This video, which I grabbed off the internet, is a very nice demonstration. You see, after the Big Bang, the universe cooled, and then all of the electrons and the nuclei combined into atoms. And in that, it was very, very dark. There was no galaxies, there were no stars. And then eventually, matter accumulated to the point where the first stars ignited in the universe. And their hot, bright emission of ultraviolet light streamed out and ionized all of the surrounding atoms, basically stripping off their electrons and making the universe transparent. And so by probing this regime, by looking at hydrogen gas at very long distances, which is equivalent to very early times in the universe, the SKA will be able to provide constraints on models like this, simulations that people have made to simulate what it was like when the first stars and galaxies formed. Now, another interesting science case for SKA is characterizing the gravitational wave background. So many of you have probably heard of gravitational waves, but they're a new way of studying astronomy, where you have massive objects like supermassive black holes that have met each other after their host galaxies have merged. They rotate around each other, and they're so massive that they cause ripples in the fabric of space-time that propagate out into the universe. This happens in millions, if not billions, of galaxies around the universe, flooding the universe with these ripples of gravitational waves. How could you detect it? Well, you could use these pulsars, which have very, very well-established periods where the pulse comes repeatedly to an incredibly high precision. The gravitational waves come by and they cause slight changes in the rotation rate of the perceived rotation rate of the pulsar because the light gets disturbed as it passes through. And then by looking at many pulsars, you can establish that gravitational waves are coming through. And this very theoretical thing was actually detected convincingly for the first time earlier this year. Because SKA will be able to see so many more pulsars over much longer periods, it will be able to establish this gravitational wave background much better, which should tell us how galaxies themselves merged in the early universe. Okay, so what is Canada's contribution to the SKA? Well, my clever colleagues in Penticton at DREO have produced these important boards, the Talon correlator boards, which form the heart of the SKA mid. It's, again, the correlator is the machine, the supercomputer that combines all of the signals together. And it does this at an incredibly fast rate. For example, these will continually process 10 terabits per second using about 300 FGPAs, which is a form of electronic chip. Now, each of these has about 25,000 multipliers running at 500 times a second. And that means combines, it basically performs 4 quadrillion calculations per second, which is unbelievable. And it does this actually at a relatively low energy rate and cost. And that's a big testament to the skill of my DRAO colleagues for producing this board. Another important thing that we will be doing is that our Canadian Astronomy Data Centre down the hill here is going to transform into a node of the SKA Regional Center network. All of that data that SKA is going to produce in huge amounts, it needs to be collected somewhere for the community to be able to download and use. And so the SKA regional centers are designed for each of the partner countries to enable their own communities to access those data. Now, this means that this amount of storage that the CADC currently has to expand almost 2 orders of magnitude in the course of a decade. Right now, the Canadian Astronomy Data Centre, which hosts full archives of Hubble, James Webb, Gemini, JCMT, CFHT, all of those Canadian observatories, in total is about somewhere in the order of about 2 petabytes, where a petabyte is about 1 million gigabytes.
Filled with servers?
No. We're contracting with an organization called the Digital Research Alliance of Canada, which is a federal funded organization for high performance computing in Canada, and they will be building the servers for it. So we don't have to build a big server farm here on the hill. But nevertheless, we have to grow quite a bit. Basically, the online storage grows from 3.5 petabytes to 42, and the nearline storage grows up to 150 petabytes by the end of the decade. That's a huge, huge amount of data storage. And on top of that, the CADC is going to grow by about 7 staff members in the short term, so including some astronomers. And on top of that, part of the funding deal, is that there will be about 10 postdocs posted in various Canadian universities as well. So this is a big shot in the arm for Canadian radio astronomy. It's a really big deal for us. Okay, so again, I mentioned the vast amount of data. The SKA low is going to produce 7 terabytes or terabits a second. That's a lot. SKA mid will produce 8 terabits a second. These get crunched in the central signal processors and then crunched again in various supercomputers, producing an annual output of about 600 petabytes, which is a lot. Again, now your laptops may have a terabyte of storage. A terabyte is only a fraction, like 1/1000th of a petabyte. So this will be filling something like 600,000 laptops a year in data. So it's quite a lot. And then the data are then distributed to these regional centers, and then people are able to work on them from their home institutions. Lori mentioned what was the engagement with the Indigenous folks. One of the interesting things that came out of our long-range plan process this year was acknowledgement of the need for consent to be provided by Indigenous communities. In fact, it is a central theme that astronomers now must find in order to continue with their research. And it includes all Canadian observatories, including this one that we're visiting right now today. But in the SKA, you can see that part of of the recommendation was that Canadian participation in it should be subject to this guiding principles for sites used by astronomy projects centered on the consent for the use of the sites from Indigenous peoples and traditional title holders. This is a big, big change in how astronomy is being done. It's much more conscious, and I think it's a credit to the panel for producing this kind of recommendation. Go ahead.
So the site that was chosen in Australia and the site that was chosen in South Africa,
Yes.
does climate have anything to do with it? Because Canada's on lots of land, but there's not much radio
Yes.
wave interfering. So is it better to have it in a place where there's no snow and there's no snowstorms? And
Absolutely, yes. I mean, in radio waves aren't as affected by weather as optical and infrared light is. It's much less affected by the presence of water in the atmosphere. But nevertheless, there are issues of radio quietness that need to be, and Canada is not as radio quiet a place as these places are. So that's the deciding factor right there. Okay, so again, the local Indigenous people are quite involved. These are the Wajari Manji people of Western Australia. These are some of their children that came to a ceremony to beginning of the construction. And on the right is a chieftain from the San and Griquaquoy people of South Africa. And again, I have to say that the people who have been involved in developing the SKA concept have been extremely proactive in engaging the Indigenous folks in what the project will mean for them. And I think it's not just to get consent now and ignore them later. The idea is that consent can be revoked anytime. So it really does mean that going forward, Canadian observatories are going to need to establish relations with Indigenous communities that are long-lasting and full of mutual benefit. Okay, so when will it all become available? So here's a wonderful slide, but it shows time on the bottom axis and the spread out into different things that need to occur for the SKA with regards to science. The yellow bar here shows where we are right now today. And you can see that just next year, the beginning of science commissioning will occur. Now, because each of the different observatories is basically a collection of antennas, you don't need to complete all of them to be able to do science. You just need some, and then you can work on building them out and starting to do science while some of them have been already fit for actual work. So the role of science commissioning is to basically shake out the antennas to see if they're working in the way that they're meant to be, and working out to see if the software works and everything is up to speed. And then just in 2027 or so is when the actual first science is going to occur. So that's very exciting. And then as the decade continues, more and more antennas are going to be added in until by about 2030 when the whole thing will be complete. Okay, so to end, I mentioned SKA2. What is that? Well, originally, SKA was meant to be a square kilometer array, and SKA phase 1 is not going to be that. I mean, the dream was to build, again, the world's largest radio telescope. It is going to be that. But in order to achieve its full potential, it needs to have even more. And so the project was divided into a phase 1 and a phase 2, where phase 1 was to get a start, get something out there that was itself scientifically interesting, with the idea that in the future, again, it can be built out to be even something more. And that's what SKA2 is. It'll basically be SKA 1 times 10. So instead of 200 antennas, it will have 2,000 antennas. And they will not be just in South Africa. They will be spread out all across the southern of the African continent. And so that will be a very exciting day when that occurs. Meanwhile, in Australia, I love this because it looks like they're growing by nanobots or something like that. But the idea is to go from like 131,000 individual dipole antennas to 1 million that are spread out across the Australian outback.
how much does it cost to build?
I actually don't know the answer to that. but it has to be relatively cost effective. These things, clang clang, are not themselves elaborate. They are just big metal things that are arranged in ways that allow the radio waves to be captured. So when SKA2 is complete, that will really show the full potential of the project. But for now, Canada is now a member of it, and we are poised to be able to continue in the project in the decades to come. So to summarize, Canada's next astronomical observatory will be the SKA Phase 1. It'll be a $3 billion multinational facility dedicated to low-frequency radio astronomy. There'll be 2 sites, an SKA Low in Western Australia and an SKA Mid located in South Africa. Canada is going to have a 6% share. There are currently, I think, about 20 countries interested in joining SKA. And we're going to be supplying the brain of the SKA Mid as part of our contribution to its construction, and also contributing to the global storage of the immense amounts of data it will produce. The early observations are coming fast, with science likely starting around 2027 or so, and then SKA2 will be an order of magnitude larger, though it may take some time to happen. But again, something to look forward to in the future. Thank you very much. I'd be happy to answer any questions anyone might have about anything I said or anything else. Go ahead.
Take that around to somebody here. Yeah. Oh, yeah. Oh, great, thanks. I'm just curious, like when you talk about the full potential, especially with SKA2, is it going to be possible for this array to hear? Like how far back? Like right now, I guess there's data coming in like from the Webb telescope that's getting pretty close to, like you talked about the cosmic dawn. Will this array be able to hear? And I don't know if it's possible to image what it hears. How close to the Big Bang can it get, do you think?
Okay, so there's a few aspects of that very excellent question that I would like to address. First, despite it being our radio astronomy, we actually do make images. We don't listen and hear these signals at all. That's sort of a common misconception because we listen to the radio, right? But what's really happening is that radio light is being beamed from the transmitter into the receivers in our radios, and then being converted into acoustic signals that we then listen to. So we actually are receiving the radio light at long radio wavelengths. And so when we look out into the deep universe, we're actually looking, we're not listening. Okay, and then how far back can we go? That's a really, really good question. So I think realistically, we can't really get much further back than the first galaxies and stars because the universe is opaque at that time. Now, there are radio observatories that look further back because there's this cosmic microwave background, which is the afterglow of the Big Bang. And there was a period of time pretty soon after the Big Bang where that emission was decoupled and allows us to see it. But that is kind of an omnipresent glow in the universe in which there are faint ripples as a result of the growth of matter. And that is really, we're already seeing that already with radio wavelengths by detecting those all over the sky. So really the goal, I think, is to look at that cosmic dawn era where the first stars and galaxies are forming. Okay?
Oh, I have another question.
Sure.
Okay. What metal are those trees made from? Is it aluminum or is it stainless steel?
That's a really good question that I don't have the answer for, but my guess is that it is made of steel. It's nothing terribly expensive. It just has to be set up in a certain configuration for us to use. You see, what happens is that the It needs to be metal because metal is filled with electrons like floating around, right? And what happens is that the radio signal comes in and it causes those electrons to move, fluctuate, right? So you need to have metal that is relatively conductive, and I think steel is probably good enough for this purpose, but I have to say I'm just taking a guess there. Any further questions? I'm happy to. Oh, okay.
No, that's okay.
It's for our people at home.
Well, this is all new to me. So does that mean we'll be able to find other life forms in the universe as well?
That's another excellent question. So one key aspect of SKA that I didn't even touch on was that there will be people who will be looking for signals from extraterrestrial intelligences. And this can be done on top of science projects that will already be ongoing because of the certain flexibility in the way that radio observatories can work is that you can have some of the radio observatory looking in one direction, but then you can also look in other directions too. And already this is happening at places like the Very Large Array, for example, and other radio observatories around the world. But the SKA will have a huge increase in sensitivity compared to those current ones. And so it will be able to listen for signals from a much greater volume of the galaxy. Still a tiny volume compared to the huge immenseness of our galaxy, but still it will push that volume to much greater sizes. Oh, and if I may also say, SKA will also be able to probe things like terrestrial planets around nearby systems and be able to perhaps look for biosignatures and things like that.
I had was, where you're setting this up is on the bottom, I think on the bottom of the Earth. Of course, it's a whole different part of the universe that we never see.
That's right.
So it's not actually going to make a big difference on what you're going to be able to perceive in the universe?
Yeah, that's another excellent question because people in the southern hemisphere can only see parts of the sky that we can't, and likewise we can only see parts of the sky that they can't because that's just the way living on a sphere works. But I will say that there actually are plans for a northern SKA-like observatory. The Very Large Array that I described before is considering an upgrade or a whole new array actually called the Next Generation Very Large Array, which will cover not all of the same wavelength ranges that the SKA will. It will be shifted to slightly smaller wavelengths, but nevertheless it will have a northern hemisphere perch and be able to provide full sky coverage at a common range of wavelengths. Yes.
So I've lived in northern Canada. So how far north would they go? Like, are they talking Nevada where the climate is rather pleasant? Or are we talking like Arctic islands where it's minus 60, minus 70, and that's going to destroy your machinery?
This is actually going to be based in the American Southwest. So the Very Large Array is currently located in New Mexico. It's all within the central part of the state. Now, the Next Generation Very Large Array will have antennas spread out all across the Southwest, from West Texas to Arizona, all the way even into northern Mexico. And then on top of that, there will be stations set out across the continental U.S. and including Hawaii and the Virgin Islands, and maybe even in Penticton, there may be an antenna placed there, and that will give it very high resolution power by having such a wide range of stations across a huge amount of, like 8,000 kilometers worth of distance between the two. Between the pairs of antennas.
They sound like the modern pyramids.
They certainly are mega projects, like the pyramids were back in the day.
Another question.
Hold on, Don has a question here. Sorry, Lorraine, I'll just get back to you in a minute.
How, if at all, will these be affected by the growing constellation of communication satellites?
That's another excellent question. So those of you who hadn't heard, right now we're in an age where tens of thousands of satellites are being launched into space to provide a global internet coverage by many countries. In fact, I read last week there are about 1 million of these satellites that have been planned so far. Now, not all of them may pan out, but that means that our perception of the night sky, for even visually, will change because much of what we can see in the night sky is stars, and soon they may be overwhelmed by actually light scattered from sunlight scattered off satellites into the night skies. This is not an awesome future for optical astronomy, but also radio astronomy too, because there may be significant radio signals from these satellites as well, whose beams will enter into the dishes and the dipole antennas of the SKA. Now, I also read a preprint last week that said that, they are already detecting these kinds of things. So it may be quite significant, but this kind of information helps us approach these companies and try to find mitigation. And hopefully by actively talking to them now, we can work to a solution that will help us all. I will say that the way radio arrays are designed, there can be ways of identifying sources of interference and canceling them out, which will be helpful, but nevertheless, it's still a problem that we'll need to be dealing with almost across all of astronomy in the next few decades. Hold on, Calvin. Lorraine.
Sure. Okay. So radio waves and ETs. So, okay. How would we know through studying radio waves that it's at all connected with ETs? And in the reverse, would they find us through radio waves? How does that work?
Yeah, it's quite possible. So people who have thought about searching for extraterrestrial intelligences have long thought that radio waves are probably the medium of choice for interstellar communication because it doesn't require a lot of energy. It isn't absorbed by intervening interstellar dust. And you can encode things in it very easily. So it checks a lot of boxes, right? And so there are two ways to communicate. One is intentionally and one is not intentionally. Intentionally means you beam a signal to someone who's expecting it. And you can basically do that now. You could beam across the galaxy if someone you knew over there was able to detect it. But right now all of our radio signals are propagating out, spilling out into the universe, and they have been over the last 100 years. And if there were instruments from other civilizations that were sensitive enough to detect this, they could then see the things that we had broadcast all that time. So who knows, maybe they're watching I Love Lucy on Vega right now. But nevertheless, I think that it is something that radio waves are considered a possible way of doing. And even like things like airport radars are something that signals that some civilizations might be able to detect, and we ourselves might be able to detect theirs for some small fraction of relatively close stars. And the SKA actually has worked out how many stars that might actually cover with its sensitivities. Okay? All right, Calvin.
Yeah. So I always wonder about these kinds of radio arrays. The field of view, is this like a big, wide, all sky survey thing, or is this going to be like pointing at specific targets?
Okay, so the different antenna arrays of the SKA will work slightly differently. The dipole arrays actually do receive signals from all over the sky, but they can be focused electronically into given directions, and so you can choose which way to look in that manner. So you can basically form a beam. It's beam forming, it's called, and you can say we're going to look over this way, and maybe also over this way. way and maybe also over this way. It's kind of cool. Now the dishes are much more directed because you point the dish in a given location or a given direction, and that way you're not looking at the entire sky. You're mostly looking in a particular direction. I will say the radio waves are a little slippery in that you can actually get signals where you're not really pointed at because of the way that the sensitivity can pick up emission from all over the sky. But nevertheless, directly, it's mostly going to be in a given location. But SKA will have so much sensitivity, it will do these very large surveys where large amounts of the sky will be covered all the same.
What would Mr. Jansky think?
Oh, I think he would be quite impressed. I mean, he's very highly regarded in the radio astronomy community. For example, they named the Very Large Array after him. That was the work of the National Radio Astronomy Observatory in the U.S. They also have a postdoctoral fellowship called the Jansky Fellowship, of which my colleague Yancey was one, who's visiting us from Arizona this week or this month. And on top of that, perhaps most notably, there is a unit of flux called the Jansky. Radio waves are so low energy that we basically have defined the amount of energy in a given range of wavelengths, basically 10 to the minus 23 ergs per second per centimeter squared per hertz per steradian is actually called a Jansky. So we actually use Janskys as a unit, like we would kilometers or inches or degrees Celsius, as a way of measuring the brightness of things. So he's... Yeah, so it is, I think he would be very impressed, you know? I mean, it's hard to know the things that you do in your day, what will happen in the future. And I think he would be probably gobsmacked to see just how much his accidental discovery uncovered. Okay, any further questions, or can I leave on that rather poignant note? Okay, thank you very much. Thank you for coming out tonight.